second lesson plan that starts with non-invertible symmetries and ends in y2 pions. Okay. This is a nice progression.
Well, hopefully I'll get to there.
Is the mic on?
Yes, it's on now. Shu-Heng, good to see you.
Yeah, so welcome to Colorado.
Thank you, thank you.
I'm going to do a reminder, but then are you good to start when that's done?
Whenever you're ready.
Okay. Give them a minute. It's the last week.
Good morning, everyone. Welcome to the last week of TASI. Hope everyone had a nice weekend. I know it's sort of that point where we've been in this room for a long time, having good lectures, but it starts to get a little stretched out by the end. So I hope everyone is, finding some time to relax now and then, stuff like that. So I want to remind you that after this lecture, we are going to do the TASI photograph. So we will all go outside, do a little walk. We usually go down to Farron Field, which is this big field you pass on the way here from the dorms. We'll take a photo there. Then we'll come back and we can have a little coffee in the second half of the coffee break. So that's right after this. So it's my pleasure to introduce Shu-Heng Shao. So as you have been reminded, there's been 3 scientific organizers for this program who picked all the other lecturers and set the program. Ken Intriligator and Ibu Ba. Shu-Heng is the 3rd scientific organizer for this school. So even though he hasn't said a word yet, let's give Shu-Heng a round of applause for the great planning of this school. And Shu-Heng is going to tell us about non-invertible symmetries. Take it away.
Right. Thank you very much, Oliver. And thank you, Ethan, Tom, for this incredible effort for putting together the TASI summer school. I just got here yesterday. I've been watching a lot of the video recording of the previous lectures online. I think they are all very fantastic. In fact, I will use many of them during the course of my lectures. So the title of my lectures will be Non-Invertible Symmetries. And this is a very rough outline. And I'm almost 100% certain that I over-prepare. So I might skip many of the topics there. But during the free time, I'll be happy to talk about things that I prepared but didn't get the chance to cover in my lectures. So let me quickly go over them. And please feel free to interrupt me with any questions anytime. So in the first part, I will give a general discussion on the difference between operators and defects. This is something that we have heard a lot throughout this whole summer school. But there are certain aspects I want to emphasize more and connect to the previous lectures. And this will be very crucial in understanding what we mean by a non-invertible symmetry. Like in what sense those operators/defects are non-invertible. Now, in the second part, I will focus on the 1+1 dimensional Ising model. In fact, when I was preparing for this lecture, I realized that I can actually spend 4 lectures just talking about the Ising model. But then I figured out, but I think that won't be too exciting for some of you. So I still want to cover some other more recent development. So let me ask, how many of you have learned Ising model? All right, that's kind of the expected answer. Great. Now, how many of you, when you first learn Ising model, you learn it as the first unitary minimal model in the spirit of BPZ? Really, no one? Seriously? I learned it that way. Okay, I was trained as a high energy physicist. I took a CFT class, and that's where I learned the Ising model. Okay, I'm being judged, I can tell. Okay, how many of you learned the Ising model from the two-dimensional statistical model first? Okay, I can see that. Now, how many of you learned the Ising model from the transverse field Ising model in the Hamiltonian formalism? Okay, yeah, that's also what I expected. And how many of you learned from the Landau-Ginsburg perspective, 5 to the 4th? Great, great. All right, so I'll try to cover most of these perspectives. And in fact, I'll mention, but not discuss in detail, 6 different constructions. 3 of them are in the continuum from the field theory point of view. 3 others are from the lattice point of view. And hopefully in this way, I can give a compelling picture on the simplest possible non-invertible symmetry of the one in the Ising model. And I think throughout this whole school, we have heard a lot of discussions of generalized symmetries in quantum field theory. There are also a lot of discussions on the lattice, in particular in Meng's lectures, in Nati's lecture, and many other lectures. And I think it's really important to have the complementary perspective on how to understand all these new symmetries, either from the lattice point of view or from the continuum point of view. I had a conversation with a very distinguished condensed matter physicist a while back, and he told me continuum field theories are not physical because you cannot put them on a computer. And then a little bit later, I talked to a very distinguished high energy physicist, and he told me lattice models are boring because you can put it on a computer and solve them. Well, in my case, I think both are too extreme, and I would like to hit the middle ground. And that's the reason I prepare these lectures on the Ising model. Great. All right, so up to this point, we are mostly in 1 plus 1D. And then I'll talk about condensation defects. It's a subject that has been invented about maybe 15 years ago in the condensed matter physics community, but has received a lot of attention in the high energy physics community as well, relatively recently. It's really the simplest possible kind of non-invertible symmetry in general dimensions. This object is like when you learn algebra. The first number you learn is the number 1. And after you fully understand the number 1, you can try to learn 2, 3, 4, and so on. And condensation defect is like a unit element in this sense. And I'll try to give some example in 2 plus 1D. But I'm actually afraid I won't have time to say a lot about it because of the time constraint. And then I'll talk about half gauging, which is a very powerful way to construct a lot of the non-invertible symmetry. And this discussion mostly will be in 3 plus 1D. And finally, I'll try to give a physical application of the non-invertible symmetries in the context of pion decays in our real world. All right, that's the rough outline. Any questions at this point? All right.
I hate to interrupt. Can you double check if the microphone is on?
Oh.
Switched off the green light.
Screen light.
Okay.
Okay.
I'm gonna adjust the sound a little.
All right, maybe I'll put it a little bit up here.
Definitely hear that it's on.
Uh-huh. Maybe, is it better now? I couldn't tell the difference.
I can, yeah, it's loud.
Okay. All right. Okay, this is the movable board. Great. All right, now let me start with the first topic, operator versus defects. Now, as we all learn in quantum mechanics, there's a Wigner's theorem. Telling us that in quantum mechanics, symmetries are implemented by unitary or anti-unitary operators. It's proven by Wigner in 1931. Now, unitary operators are those that obeys the conditions that its inverse is its dagger. So in particular, unitary operators are invertible. And the mathematical theory for describing symmetries in quantum mechanics is group theory. So that's all good in quantum mechanics. But in these lectures, we'll mostly focus on quantum field theory in higher than 0 + 1 dimensions. Now, in quantum field theory or lattice models, in greater than 0 + 1D, there's something new when we talk about symmetries. And the new concept is that now we have a notion of space. And spatial locality plays an absolutely important role throughout the discussion. And the notion of spatial locality gives important constraints. And more possibilities for symmetries. And I'll explain exactly what I mean later on. As a result, there are many generalizations of the ordinary symmetries that we are familiar with when we come to quantum field theory. And I'll mention two of them. And there are even more complicated generalization or kind of fusion between the two generalizations. But let me be simple-minded and start with two generalizations. Now, the first one is the one that I'm sure all of you have heard a lot in the past 3 weeks, which are the higher form symmetries. Higher form symmetries act on extended objects in space, such as Wilson lines in gauge theory. And this is something you don't have in quantum mechanics. In quantum mechanics, you don't have the notion of space. You don't know what is extended and what is not. Only when you go to quantum field theory or lattice model of higher dimensions, you can meaningfully talk about higher form symmetries. So this is the first generalization. Now, the second generalization, which is the main topic of my lectures, is that there could be non-invertible symmetries. And these are symmetries without an inverse, as the name suggests. And there has been a lot of development on these two kinds of generalizations in the past decade. There's a lot of combination of the two and examples discovered on maybe a weekly basis recently. And it's calling for a new mathematical structure. To describe these new symmetries. And very roughly speaking, it should be the category theory. Now, this is a big subject. There's a whole community of mathematicians and physicists working on category theory, and I'm sure you have heard a lot of them in this school. And in particular, in Meng's lectures, he talked about fusion category, talked about braided fusion category, modular tensor category. And there are examples of the mathematical language of category theory to describe new symmetries. Now, in my lectures, I'll try to stay away from using this mathematical language because the first thing is that Yifan and Meng already talk a lot about fusion category and braided fusion category, and I don't want to repeat them. And second of all, I want to give some complementary physics picture attached to this mathematical framework. All right. Now, up to this point, it's still very abstract, and you might wonder, what is a non-invertible symmetry? In fact, you shouldn't be surprised that there are non-invertible symmetries. We have all seen various kinds of non-invertible symmetries, but they're a little bit stupid. So let me give a stupid example. All right. So consider a quantum mechanics model. Now, I just said we have to go to quantum field theory to meaningfully talk about non-invertible symmetry. But here I start with quantum mechanics. And you will soon see why this example will end up being stupid. Consider quantum mechanics with a Z2 symmetry. And it's implemented by a unitary operator U, which squares to 1. Right? So for instance, the simple harmonic oscillator has a Z2 symmetry. And U, being a symmetry in quantum mechanics, at the very least, should commute with your Hamiltonian. And in quantum mechanics, there's pretty much nothing else you can ask for. You have a Hamiltonian, you have an operator that commutes with it. By all means, it should be called a symmetry. Whenever you have a Z2 symmetry, we typically define the operator P in the projection. It projects to the Z2 even state. P also commutes with the Hamiltonian. So we should probably think about it as a symmetry. But P doesn't have an inverse because P has a kernel. When you take a Z2 odd state, P will annihilate it. It has a 0 eigenvalue. Does not exist. So it's an operator that commutes with the Hamiltonian, and yet it doesn't have an inverse. But when you first learn the projection operator, you don't go around and tell your friends that you find the non-invertible symmetries. And the real reason is that you know it's made out of the unitary symmetries that you start with in the first place. It's kind of like a derivative object. You know there's a U. There's nothing funny about U. U squares to 1. U maps an operator to another operator. It commutes with the Hamiltonian. Now you use this U and to take a linear combination of them and find something that has a kernel. Here it's important that we are able to take the linear combination, and that's the beauty of quantum mechanics. In quantum mechanics, if you have two states, you can consider a superposition of those two states. Schrödinger's cat can be both alive and dead at the same time. Now, it's precisely because of this plus, now you can consider operators such as projection, and they are sometimes non-invertible. But I would like to emphasize that they are not that interesting because they are made out of invertible symmetries. Later on, when we go to higher dimensions, so 1 plus 1D, 2 plus 1D, and higher, we will see genuinely non-invertible symmetries that cannot be written in terms of invertible ones. And here, I would like to add a side comment that later on when we talk about condensation defects, you should try to remember this discussion we just had. In many ways, condensation defects in higher D are like the higher dimensional analog of projections. This comment hopefully will become clear in later lectures. Okay, I'll move to this board. Any questions at this point? So far, I think, yeah, please. Not necessarily, sorry. So the question is that, is any non-invertible operators in quantum mechanics that you can cook up, is it always the projectors? I'm not exactly sure, but I don't think that's true because we're just talking about matrices, right? So it's just about matrices with a zero eigenvalue. Maybe that's the definition of projection. I'm not sure, but there might not even be invertible symmetries underlying. In quantum mechanics, the structure of the symmetry is just that you have matrices and they form an algebra. You can add them with arbitrary complex coefficients. Any other questions? Okay. All right, so that's in quantum mechanics. And now we are going to move to quantum field theory or lattice model in higher D. Mostly I'll focus on quantum field theory. So for this part of the discussion, I'll be focusing on relativistic quantum field theory. And we're in D space-time dimensions. Okay. Now, let me start with a simple example of a global symmetry in general quantum field theory in diverse dimensions. This example has appeared in previous lectures, but let me just repeat them. So suppose you have a conserve Noether current J mu of x. It's a local operator with a vector index. Conserve meaning that its divergence vanishes, or we can write it in the differential form notation. Here I view J as a one form, and star is the Hodge dual of a differential form. Now, given such a conserved current, you can build an operator U theta. Where we take the time component of the current, integrate it over the whole space. We're in D space-time dimensions, so the number of dimensions for space is D minus 1. This object, U theta, is supported at a given time and span over the whole space. Therefore, it is an operator. It's an operator acting on the Hilbert space. You quantize at a given time. The fact that the current obeys these local conservation equations implies that this operator is invariant under time evolutions. Or if we write it in a more quantum mechanical language, it commutes with the Hamiltonian. All right. And you pretty much say the same thing in quantum mechanics. You have an operator and it commutes with the Hamiltonian. By the way, just for the sake of terminology, I usually call this thing, well, I think it's usually called a charge Q. Now, for U1 symmetry, the symmetry operator, the unitary operator that implements the symmetry is the exponentiation of the charge with a rotation angle theta. So throughout the lecture, we should distinguish the charge versus the unitary operators. Now later on, we will talk about non-invertible symmetry, and they will not be unitary, so I will call them symmetry operator. Okay. So far there's nothing new in quantum field theory. We have an operator, it acts on your Hilbert space. If you take the space to be very small, you are effectively going back to quantum mechanics. Now, in relativistic quantum field theory, you should find this expression over here a little bit disturbing because it's not covariant. It's not written in a covariant form. Now, it can be made covariant, and this formula has appeared previously. Now, in Euclidean space-time, you can pick any closed d-1 dimensional manifold M and define the integral this way. J is a 1 form, star J is a d-1 form, and therefore you can integrate it on any closed d-1 dimensional manifold. Now d star J being 0 now implies this new object U theta of M is invariant under small deformation of M. In particular, when M is the whole space at a given time, you can move it a little bit in the time direction and you won't change any correlation function. And this just follows from Stokes theorem. So in a sentence, we say U theta of M is topological. And you should really view the word topological just as a suited version for conservation or conserve in relativistic quantum field theory. But what is this object U theta of M? If you're a Euclidean person, then you don't really care. There's no notion of space versus time. Every direction can be taken to be your Euclidean time. Any direction can be taken to be your spatial direction. And you compute Euclidean correlation functions, and you try to compare different Euclidean correlation functions with different operator insertion. In one Euclidean correlation function, you take M to be one manifold. In another, you deform it a little bit, and you try to compare their values. These are meaningful things to do. But once you go to a Lorentzian picture, it makes a difference on which direction you pick to be the time direction. So for instance, let me draw the picture here. Let's say we are in two space-time dimensions. And our space-time says is a torus. So here our space is a circle, and this is the time direction. I may or may not want to identify the Euclidean time direction at the end of the day, but let me just draw it that way. Now I can take my U theta, I can take my M to be the circle in the x direction. In this way, it's over here. It's an operator at a fixed time acting on your Hilbert space. Alternatively, you can take M to be along the time direction. And let's say I compactify the Euclidean time direction. So these two objects, there are two specializations of this more general formula. But they mean something very different in quantum field theory. The first is an operator acting on the Hilbert space. And the second is a defect. Now, what do I mean by a defect? A defect is something localized in space and extends in the time direction. What it does is that it changes your quantization. Originally, when you quantize the system on a S1, you get a Hilbert space H. For instance, maybe you have a complex scalar field, a free complex scalar field theory. There's a U1 symmetry rotating the complex scalar by a phase. And here you just impose a periodic boundary condition for the complex scalar field. In this case, you insert a defect labeled by some angle theta, meaning that your field, as it goes around the circle, is no longer periodic, but the boundary condition is twisted by this symmetry. And therefore, you get a different Hilbert space, labeled by the defect. And this is not something advanced or sophisticated. These are just two different boundary conditions in the simplest example. Any question at this point? And one thing I want to emphasize is that this, the second line over here, is something really new in quantum field theory, something you didn't have in quantum mechanics. In quantum mechanics, you just have operators. There's no notion of space. You cannot talk about defect. Once you go to quantum field theory in higher dimensions or lattice models in greater than 0 plus 1D, you can talk about objects that are localized in space and changes your quantization. It gives you a different Hilbert space. And it's precisely the interplay or the relation between operator and defects that will become important when we talk about non-invertible symmetry. So here's a general principle, or maybe a slogan. In quantum field theory, every symmetry serves at least two purposes in life. One, it leads to, I have to bring my blue chalk. It leads to a conserved operator acting on the Hilbert space. Second, it leads to a topological defect that changes the quantization and give you a different Hilbert space. Actually, let me add here. Every symmetry, let's say it's invertible, so it's on G in some group, capital G, then give you a Hilbert space H sub G. And the fact that every symmetry has to serve both purposes will give important constraints on the allow generalized symmetries in quantum field theory. Now here, let me make a quick comment. This is supposed to be true, not just for ordinary zero-form symmetry, but also for higher form symmetry. There's, however, an exception. The exception is that in d space-time dimensions, if you consider a d-1 form symmetry. Now let's do the counting. It's always confusing to count the degree for a higher form symmetry. If you have a d-1 form symmetry, in d space-time dimensions, the symmetry operator that implements the symmetry transformation will be a point in space-time. And for this kind of symmetry, it certainly can serve as a conserved operator acting on the Hilbert space. However, you cannot use it to twist your Hilbert space because it can never extend in the time direction. If you recall that in that picture, a defect is something that has to be extended in the time direction so that it modifies the Hilbert space, not just at one time, but in all time. So, but for d-1 form symmetry, it's a point in space-time. So it cannot serve the purpose as a defect. So this principle doesn't apply to d-1 form symmetry. And the simplest example is to take d to be 1. And then we're just talking about zero-form symmetry or ordinary of symmetries in quantum mechanics. And indeed, there's no notion of defect in quantum mechanics. And this will be important later on. We'll see that because of this, there's no interesting non-invertible symmetry for d-1 form symmetry in d space-time dimensions. There are also exceptions in fermionic theory, but let me not comment on it. All right. So far it sounds very abstract. Let me connect this discussion to Yifan's lecture. Actually, yeah.
Would say if like I pick the diagonal S1, like twisting in both directions?
Yeah. So the question is that what if you take the defect to be along the diagonal S1? Yeah, you can do that. Or let me phrase it more invariantly. We're on a torus. In torus, you have various different cycles. Let's call this A cycle. This is B cycle. A cycle is the spatial direction. B cycle is the time direction. You can also wrap the defect around the A plus B cycle. That's something perfectly legit to do. In fact, what I will give you is a symmetry operator acting on a twisted Hilbert space. So it's something more advanced, but it's a consistent Euclidean configuration, and it defines a symmetry operator in, it defines a symmetry operator here. Is that clear? Because if you wrap the A plus B cycle, that means in addition to the red line, you also have a line here. So it's an operator acting on the twisted Hilbert space. Yes?
What if I do something more annoying, where I go up the A cycle for a bit, and then I stop going up the A cycle, go around the B cycle for a bit, and then go back up the A cycle?
Yeah, that would still be a, say again. So you have a single defect, just one type of defect. Yeah. And please.
And it goes up the A cycle, like halfway, it goes halfway around the torus on the A cycle, goes halfway around the B cycle, yes. Goes halfway around the A cycle, and goes the other half of the B cycle.
Okay, I'm having trouble understanding it in real time. But no matter what it is, it will give you some operator acting on some twisted Hilbert space. Yeah, I hope, yeah. And maybe after the class, you can draw it to me, and I'll understand better what you mean exactly. Any other questions? Sometimes it might be a composition of two operators in the twisted Hilbert space, but then you can compose them, and that's another operator on the twisted Hilbert space. Okay. Oh, yeah.
So what do you mean by conserved operator?
Right, okay, so by conserve, I mean something that commutes with the Hamiltonian, or in quantum field theory, it will commute with the stress tensor. Right, so usually when we use the English word conservation, it means that it's invariant under time evolution. And that's what I meant here. Any other question? Okay. So let's put this abstract discussion, because so far it sounds that I'm just saying something tautologically true. But let me put it into context and go back to Yifan's lecture and see how this operator versus defect picture constrains the possible symmetry over there. And that brings us to one of the 6 ways to construct a non-invertible symmetry in Ising CFT, which Yifan already covered. So recall that in Ising conformal field theory, we have 3 Virasoro primaries. And they are the identity operator, the epsilon operator, the sigma operator. Their conformal weights, h comma h bar, 0, 0, 1 half, 1 half, 116, 116. Any other states or operators are descendants, are Virasoro descendants of these 3 primaries. Now, symmetries by definition commute with the Hamiltonian, and in quantum field theory, it should better commute with the whole stress energy tensor. Virasoro generators are descendants of the stress energy tensor. So once you figure out how the symmetries act on the primaries, you don't have to do any work on the descendants. The symmetries have to act in the same way on the descendants as their primaries. Otherwise, the symmetry won't commute with the stress energy tensor. So all we have to figure out is what are all the possible generalized global symmetries act on this 3 particular states. Okay, so if I talk about the operator state correspondence, so each of this operator, well, actually, let me just write them as state. So the possible generalized global symmetry can act on this 3 states with some eigenvalues. So L acting on 1 can have L0 eigenvalues, L1 half eigenvalues, L1 16. And by that, I mean L acting on 1 is L0 acting on 1, and so on. So pretty much all you have to do is to figure out these 3 numbers. Now, in quantum mechanics, that's basically the end of the story. Oh, sorry, yes. Yeah, well, so far I'm viewing L as an operator acting on the Hilbert space. So L is one example of this object. Right? Usually when you talk, yeah, it's an operator that spans over the whole space at a given time. And in Euclidean spacetime, it will be a line operator or defect. Okay. If you take the circle to be very small of the Ising CFT, it's effectively a quantum mechanical problem. And then basically every L will do the job. You just pick any 3 numbers, and that will give you a consistent symmetry that commute with the Hamiltonian. But in quantum field theory, and in particular in CFT, you have to demand further constraints on L's. And that comes from viewing this L not just as an operator, but also as a defect. So let's see how it works. Let's see how much space I have. So let's take the Euclidean spacetime to be a torus. I'm showing the torus as a square where I identify this 2 sides and this 2 sides. This is a trace. The Euclidean partition function is traced over the Hilbert space of Ising CFT. Is q to the h minus 1 over 48, q bar, h bar minus 1 over 48. And Yifan has already taught us that the final answer can be written, I need another line, can be written as chi0 of tau quantity square, chi1 half of tau quantity square, plus chi16 tau quantity square. All right. Next, we are going to insert this hypothetical generalized global symmetry operator. And that goes back to the earlier question, that here we're viewing it as an operator. So this we choose to be the time direction, this we choose to be the space direction, and this is an operator that I call L acting on the Hilbert space. And this partition function is a trace over the original Hilbert space H. With L here, Q to the H minus 1 over 48, Q bar to the H bar minus 1 over 48. And you just get L0 chi 0 of tau square, L1 half chi 1 half of tau square plus L116 tau square. This is an explicit function of tau and tau bar. You can put it on Mathematica or whatever and play with it. Now, the non-trivial constraint coming from the operator versus defect picture is that if you view this as a Euclidean partition function, you can take this to be the time direction, this to be space, or alternatively, you can do a 90-degree rotation. And that is known as the modular S transformation. So you start with a Euclidean configuration. You haven't made any commitment on which direction you take to be space, which direction you take to be time. You make one choice, such as this one. You compute the partition function. Now you tilt your head 90 degrees around, you get a different perspective. And now you want to get a consistent answer. It's going to be the same function of tau and tau bar, but written in terms of a new variable, tau tilde. And now in this dual picture, L is a defect rather than an operator. And this Euclidean partition function is now a trace over a different Hilbert space with a different modular parameter. Now, a priori, you might not know much about this new Hilbert space. It's a different Hilbert space than the original one. Now the quantization is twisted. But one thing you do know is that it better be decomposable into Virasoro characters with non-negative integer coefficient. Because this represents the number of states, or number of Virasoro primaries more precisely, in the twisted Hilbert space. And it's this integer integrality condition that greatly constrains these three real numbers, L0, L1 half, and L1 over 16. Now, for those of you who have studied Cardy's construction of boundary condition in conformal field theory, is closely related to this argument. So sometimes it's known as the Cardy constraint, although that was usually reserved in the context of boundary condition. And Yifan gave a very nice homework for you to figure out what are the possible L0, L1 half, and L1 over 16. And to work that out, you only need to know, oops, I'm sorry, here there's a typo. This is the dual modular parameter. You only need to know how the chi's transform under tau goes to minus 1 over tau. You get a 3x3 matrix. And you can show, it's a very easy and nice linear algebra problem, that you can show that there are three symmetries in Ising's. There's the identity one, which corresponds to L0, L1 half, 16, 1, 1, 1. That's obvious. There's a Z2 symmetry that corresponds to 1, 1, minus 1. And this is completely expected because the 1/16 guy is the spin operator, the order operator, and that's the only Z2 odd operator. Now, the nice surprise is that there's another one. There's a third guy, which is usually denoted as D or maybe N. So in my lecture, I will use D because somehow in higher dimensions, we use D more often. But I think it was called N earlier in Ivan's lecture. Now D acts in a more interesting way. It acts with the square root 2 on the identity, acts with a minus square root 2 here, and there's a big 0 when it acts on the order operator. You can show that every other consistent L0, L1 half, L1 16 obeying the operator / defect constraints will be a non-negative linear combinations of these three solutions. Right? So these are three solutions. Given these three solutions, you can add the two of them. That will still give you another solution. You cannot subtract two of them. Right? If you have a solution, you multiply the solution by minus sign. Let's say I put minus, minus, minus here. Then you violate this condition. Note that it's very important that here the signs are fixed. It doesn't make any sense to have -5 state in a Hilbert space. So the allowed operations you have, which I'll say more in just a minute, is that you can take any solutions, take any non-negative integer linear combination of them. It's a very simple linear algebra problem to show that every other solutions are generated by these three. And that was our first incontents of the non-invertible symmetry in the simplest possible quantum field theory of all, Ising CFT, where you realize that there's an operator D that acts on the three Virasoro primaries with these eigenvalues, and it's consistent with the defect picture. It's non-invertible because of the big 0 here. It has a kernel. Now, from these eigenvalues, you can easily derive the fusion rule. So let me just repeat what I just said in words. More generally, given a set of such operators / defects or symmetries, so I call them dA with some index A. Let's say A is finite. What are the allowed things you can do? Well, you can multiply two of them. That will give you another symmetry. In the case of invertible symmetry, you multiply, that corresponds to the group multiplication. Or you can take the sum of them. And recall, the most important thing of the general principle we outlined there is that every symmetry is associated with a Hilbert space. dA and dB each is associated with a Hilbert space HA and HB. Their sum, naturally, is associated with the Hilbert space, the direct sum Hilbert space. More generally, because you have the sum, now you can define any non-negative integer linear combination of them. In higher D, there will be even more generalization, but let me not get to that. But what you cannot do, you cannot take the difference between them. The difference, of course, is a perfectly legit operator acting on the Hilbert space. In quantum mechanics, if you have a conserved operator, you multiply it by I, you multiply it by 1/7, you take the difference between two conserved operators, they still commute with the Hamiltonian. But in quantum field theory, this generally does not make sense because it might not lead to a consistent defect, giving you a consistent Hilbert space. You also cannot divide your operator or defect by an arbitrary number. And this is related to the fact that while you can take the direct sum of Hilbert spaces, generally it doesn't make sense to take the direct minus of Hilbert spaces. You also cannot divide the Hilbert space by 1/7. So the allow operation is very restricted. So coming back to the, actually, I just erased it. So in quantum mechanics, we said that projection is is a non-invertible symmetry. But now you know that in quantum field theory, this division by 2 is generally problematic. Because as we said, you cannot arbitrarily divide a symmetry by 2. You can take the sum, that's no problem, but you cannot generally divide it by 2. Later on, we'll talk about the condensation defects, where there's a fixed rule for what you can do. Now, related to this point, if you just look at these 3 solutions, you might say that, oh, D is non-invertible. All right, that looks funny. But if I'm just a quantum mechanical person, I can define a different operator, D prime. Let me write down the precise coefficient. All right. Now this guy, with a little bit of algebra, you can show that squares to 1. So D prime is a perfectly legit invertible operator. And you can express D in terms of D prime. And you can say that, I'm not going to think about D at all. I'm just going to work with D prime. And then everything is invertible. D prime is invertible, eta is invertible. And I never have to listen to these lectures. Now, I claim D prime is not a legit or a valid defect in relativistic quantum field theory. Because you divide a valid defect by square root 2. You also divide something by 2. You also have a minus sign. So in a general Euclidean configuration, if you make a cut, this will not give you a consistent Hilbert space. And that's why it's important to work with the non-invertible object. And this restriction from what you can do and what you cannot on symmetries in quantum field theory is really important, is the fundamental reason why we have interesting non-invertible symmetries in higher dimensions. All right, so that basically concludes the first topic that I would like to cover. If there's no more question, I will move on to more about this non-invertible symmetry D in the Ising model. Yes, please.
So is it a coincidence that the Ising has 3 Virasoro primaries and there are 3 defect lengths? Does this generalize?
Yeah. So the question was, is this a coincidence that we have 3 generalized symmetries, and also we have 3 Virasoro primary operators? And the answer is that this is something more generally true in diagonal rational conformal field theory. Yeah. This is a paper by Petkova and Zuber, from 20 years ago, that they show that in every diagonal rational conformal field theory, the number of generalized global symmetries that commute with the extended chiral algebra is the same as the number of Virasoro primaries. In non-diagonal rational CFT, the numbers will not be the same, and there's an interesting twist. But let me just emphasize that these are just symmetries that commute with the extended chiral algebra. In Ising, it doesn't make any difference because there's no extended chiral algebra. You just have the Virasoro, and that's it. If you talk about West-Zumino-Witten model, I guess we didn't cover that in this school. If you talk about West-Zumino-Witten model, in addition to the Virasoro chiral algebra, you also have a current algebra. And the analogous construction will only give you finitely many generalized symmetries that commute with the current algebra. Okay. For instance, in an SU2WZW model, you have the full SU2 global symmetry. Well, to be more precise, SO3 global symmetry. And there are infinitely many of them, whereas you only have finitely many current algebra primaries.
So can we see that just from this S invariance equation, or is it more complicated?
In that reference I just mentioned, it was derived using the modular constraint. Any other question?
About 15 minutes.
Great. Yeah. All right, so now let's move on to part 2, Ising model. As I said, Ising conformal field theory, or the critical Ising model, is the simplest possible quantum field theory with a non-invertible symmetry. So I think it's really important that we understand this example perfectly well before we go to the higher dimensional examples. As promised, I will talk about 6 different constructions. So let me start with the first one. The first one is in terms of topological lines in CFT. And this was mainly covered by Yifan's lecture. Also, the analysis we perform over here is of the same spirit. So I will not repeat this construction. Let me just say a few words. The idea is that you view the CFT from a more bootstrappy way. You know, one way of thinking about conformal field theory is not to start with some particular Lagrangian. You think about CFT as some abstract data of local operators with their 3-point function, OPE coefficient, etc. And you try to solve infinitely many bootstrap equations and get a consistent solution. Usually people only do that for local operators. But you can also throw in extended operators, such as line operators / defects. Then you will have more constraints, more equations to solve. And Yifan already talked a lot, and also in Meng's lecture, talked a lot about the basic axioms we expect for the topological lines in 1+1 dimensional conformal field theory. And by solving those constraints, you can derive all the Euclidean correlation function involving these generalized symmetry lines. Okay. So one constraint, for example, is this constraint over here. So that's the first approach. But the first approach is a little bit abstract. You know, just like the way you think about local operators in this philosophy of the CFT. You don't care where it comes from. You don't have a particular microscopic realization that you're committed to. This approach is very general because of that. You don't have to commit to a Lagrangian. You don't have to commit to a lattice model. It's completely universal. Whatever answer you get is the universal answer that can be applied to any microscopic realization of in the same universality class. While that is an advantage, it's also a disadvantage because it makes it less explicit. Now, for the particular case of Ising model, there are other ways to understand this non-invertible symmetries. So that's the one I will spend quite a lot of time on, which is to understand it from the Majorana CFT point of view. And I'll say more about that in just a minute. The third way that I will introduce the non-invertible symmetry in Ising model is from what is now known as the half gauging. And you will use the Kramer's Wannier duality of the Ising model. The third way turns out to be an extremely powerful way to construct non-invertible symmetries in general. In fact, this method will be applied to QED and QCD in 4 space-time dimensions in the second half, well, in later lectures. So these are 3 continuum ways to understand the non-invertible symmetries. There are also many lattice ways to understand the non-invertible symmetries. But for the lattice ways, there are many different lattice realizations of the Ising model, of the Ising critical point. So it really depends on which starting point you pick. Now, one starting point is the transverse field Ising model. I will spend some time discussing how you realize the non-invertible conserve operator in the transverse field Ising model at the critical point. This is a Hamiltonian lattice model acting on a one-dimensional chain in space. There are two other realizations that I will not discuss. One is in terms of the so-called anionic chain. It's a different Hamiltonian lattice model, but it also gives a way to realize the non-invertible symmetry. Then there's a statistical way to realize the non-invertible symmetry in a paper by Assen, Fendley, and this is a Euclidean lattice model. So we have already talked about this one. I will now talk about this one, and then this one, and finally this one. All right, I have about 10 minutes, so let me continue. Any question about the plan? Okay, great. All right. All right, so I will start with a discussion of bosonization. And the first thing I'm going to say, which is arguably the most important thing for this approach, is that on the one hand, there's a conformal field theory known as the Ising CFT. Ifan spent a lot of time talking about it. This is the first minimal model. So let me write it. The first unitary minimal model, the 3,4 minimal model. On the other hand, there's a Majorana CFT. Now, how many of you have studied the relation or the relation between the Majorana CFT and the Ising CFT? Okay, great. It is often stated that Ising CFT is the same as the Majorana CFT. And the first message, and probably the only take-home message, is that they're not the same. Okay. And it's exactly the difference between them that will give you the non-invertible symmetry. Now, why are they not the same? So what is a Majorana CFT? That's actually a very simple thing to write down. You're in 1 plus 1D, and the Lagrangian, let me make sure the factor of 2. Okay, the Lagrangian is chi left. So you have two Majorana-Weil fermion fields, chi left and chi right, where in 1 plus 1 dimensions, the spinor representations in 1 plus 1 dimension, the minimal spinor representation in 1 plus 1 dimensions is a Majorana-Weil fermion. It's a chiral real fermion. There are two such representations. One of them is left moving, the other is right moving. Note that this is different from 3 plus 1D. So I call the left-moving guy chi left, the right-moving guy chi right. This you can think about dt minus dx is just the 1 plus 1D version of the Dirac operator, except that you don't have to deal with any matrices because the minimal representation is one-dimensional, and you can just write it as a scalar. So this is a free Majorana CFT. You have the left component, you have the right component. The theory is non-chiral. There's no mass, they're massless. There's no interaction. And you can literally solve them. You can compute any correlation function you want. It is often stated that Majorana CFT is the Ising CFT. In fact, sometimes you can ask people, well, Ising CFT is the simplest possible quantum field theory of all. But do we have a Lagrangian for the Ising CFT? That's a tricky question. You can say that the Landau-Ginzburg 5-4 theory is a Lagrangian for the Ising CFT. But that's not strictly speaking true. It's a UV realization of the Ising CFT, and it flows to the Ising critical point. But at the critical point, there isn't quite a satisfactory Lagrangian formulation for it. Some people might say, oh, it's the same as the Majorana CFT. So just take this Lagrangian, and that's it. That's not quite right, and hence the inequality. And let me explain why that is not quite right. For two quantum field theories to be the same, they better have the same global symmetries. We should think about, I think, throughout the whole school, we are thinking about generalized global symmetries as some additional ID number for a quantum field theory. Two different quantum field theories, they might share some of those global symmetries. Maybe they both have a Z2 symmetries. But if you check enough ID numbers, you will be able to distinguish them. Let's try to apply the same philosophy here. Now, what is the invertible global symmetries of the Ising CFT? So I heard Z2, and I think that's the right answer. So the invertible symmetries is just a Z2. And that's manifest in almost all the realizations of the Ising critical point. If you realize it as a lattice model, you have a spin flip symmetry, and that's a Z2 symmetry. Importantly, there's only one Z2. You don't get two Z2, right? In the Ising statistical model, you just have one spin. There's no two Z2. Now, what's the global symmetries of the Majorana CFT? Yeah, there are two Z2s because you can flip the sign of chi left, or independently, you can flip the sign of chi right. So let me code in -1 to the f, which flips the sign of both of them. And there's another one, which, whose generator I can take it to be -1 to the f left, which only flips the left-handed one. Now, of course, I can compose them, then I get -1 to the f right, which only flips the sign of the right moving guy. So you see that the global symmetry is Z2 cross Z2. And here it's only Z2, because remember the analysis we did here. You only found a single Z2. There isn't a second Z2 for the Ising CFT. So given that the two theories have different global symmetries, there's no way that they are the same. So that's the first argument, that these are two different conformal field theories. Now, more fundamentally, there sounds a very important distinction between the two conformal field theory. Ising conformal field theory is known as it's a Bosonic CFT. Or in a more technical term, you would call it a non-spin CFT. Meaning that it's a conformal field theory that when you try to define it on a general space-time manifold, you don't have to pick a spin manifold. Spinners cannot be put on a general Riemannian manifold. There are restrictions on the Riemannian manifolds for you to be able to put a spinner on it. Those manifolds that you can put a spinner on is known as the spin manifold. If you talk about Ising CFT, you don't care about this. You don't need to pick a spin structure. You don't care if the manifold is spin or not. You put Ising CFT on it, you get the answer. Majorana CFT, on the other hand, is a fermion CFT because it's made out of fermions. So it's a fermionic CFT. Or more precisely, a spin CFT. It can only be placed on manifolds that emit a spin structure Furthermore, when you put it on a spin manifold, you have to tell me what the spin structure you pick for this manifold. By picking different spin structure, you get different answers. Spin structure is a fancy word for the boundary conditions for the fermions. So even the input data or the allowed manifolds you can put these two theories on are different. For instance, if someone asks you to compute the torus partition function of the Ising CFT, that's a well-defined answer. There is a unique answer, where is it? Oh, which is given here. But if someone asks you to compute the torus partition function of the Majorana CFT, there isn't a unique answer. You have to tell me the boundary condition of the fermions. There are actually 4 answers, depending on whether the chi's are periodic or antiperiodic. You might say the same for the Ising. You can say, oh, for Ising, maybe I can use different twisted boundary condition. But the point is that in Ising, there's a natural zero. There is a sense that this is the most elementary torus partition function with no twist whatsoever. But when you work with a spin theory, when you work with a Majorana CFT, there's no invariant sense that one choice of the boundary condition is more elementary or more natural than the other. And that's why when you talk about the partition functions of a Majorana CFT, say on a torus, there are several different answers. So even the observables are different. So I think this is a good place to end. So I'm going to stop here, where I think the most important message is that they are different. In the next lecture, I'm going to tell more how to relate them. They are different, but they are related. And the relation will help us discovering the non-invertible symmetry. All right, that's it for today.
We're going to do the photo now. I'm going to suggest we save our questions for Shu-Heng for later on. So let's all come out here and we'll head. Oh, wait, Ethan has something to say.
Yeah, we can actually have a couple of questions because we're not doing the photo now. We're going to do it on Thursday morning instead. So Thursday morning at 10:15 is going to be the photo. So questions before we start the break?
Yes.
I have a naive question.
Yes, please.
How is higher dimensional lattice model sharply different from 0 plus 1D quantum mechanics? For example, if I have L spins, I can write it as a 2 to the L dimensional matrix and everything like that.
That's an excellent question. So the question was, if you think about some higher dimensional lattice model, how is that different from just a quantum mechanical model? And how should we think about the symmetries there? Because I made a big deal out of the difference between quantum mechanics and quantum field theory. And that makes sense in the context of continuum field theory. But if we go to lattice models, then and you are right that there's a finite dimensional Hilbert space if you take all the degrees of freedom to be spins. And you can just forget about the notion of spatial locality and treat it as a quantum mechanical problem. Now, I don't have a full answer to this question, especially in the context of lattice model. I think the answer is that you have to enforce the locality in a meaningful way. Of course, you are entitled to forget about the notion of spatial locality and treat it as a quantum mechanical problem. But then you are not doing justice to the fact that it's actually a higher dimensional model. Exactly how you impose the locality constraint in a lattice model, I think depends very much on the context of your questions. For instance, how do you impose such a condition, or is there an analog of such a condition for a lattice model? I think that's an interesting question. I'm actually working on something related. I don't have a full answer. And I think it's a much more trickier question. There's still, I should say, there's still some relations on a lattice. There's still some relations between the conserved operator and the symmetry twist of a lattice model. On a lattice, you can still talk about conserved operators, obviously. You can also talk about the twist implemented by a symmetry operator, say locally in your Hamiltonian. There's still a relation between them, but the relation is not as direct as the one we have in continuum field theory. In continuum field theory, all you have to do is to tilt your head by 90 degrees, and then you change the direction of time versus space. But in lattice model, you have to do more work. Yes?
So when you say that the global structure is different, so that those are two different theories, does that mean you can't think of them as different boundary theories for the same bulk TQFT?
Okay, so I think these are actually two questions. So the first question is that, the first question is, do they only differ in their global structure? The second is that, can I view them as the boundary of the same bulk 2+1D system? The first question has some kind of intrinsic ambiguity because it depends on what you mean by the global structure. Do you consider the set of local operators of a conformal field theory the global structure? That's a paradoxical sentence because we're talking about local operators, so we usually don't think about it as a global structure. But let me just point out that, let me ask, what are the local operators in a Majorana CFT? Well, chi left written here looks like a local operator. Chi right written here is also a local operator. These are the local operators, the local fields participating in your Lagrangian. Is there such a local operator in Ising CFT? Well, there isn't, right? I listed the 3 local primary operators over here. You don't see chi left, you don't see chi right. So already at the level of the spectrum of local operators, these two theories are different. Okay. Having said that, they are still related by some global manipulation, which I'll talk about in the next lecture. Now, coming back to your second question, both of them can be realized as the boundary of the same 2+1D system. But that's not a surprise. You have, if given a 2+1D system, you have infinitely many boundary conditions that you can impose. And these happen to be 2 different boundary conditions. Any other questions? Yes.
So, question on this lower corner of the middle board. So you have this here. So I can understand what it means to what it means to multiply 2dA. But what does it mean to get a sum of that?
Yeah, I should have explained that more. So the question was, how do we define the sum over here? Now, the sum is defined the following way, and it's from a Euclidean point of view. In the Euclidean picture, the observable you have, so you have some Riemann surface, and you can insert various local operator, and say even topological lines. And this gives you some consistent Euclidean correlation function that you can compute from the input data.